Okay, so in a few minutes, we'll be starting the presentation by Waterloo. As I said earlier, it's on their air brake system and altitude control. Okay, so for those that had the chance to go at their booth, they actually have the physical air brake system, so that's pretty cool. And those that haven't had the chance, I recommend you go after. It's pretty neat to see what they're going to be presenting here, which is the active altitude control system, which is the air brake. Seeing the physical model of it is pretty nice. And they have it mounted in the rocket, and then also on the side is their outreach activity with a little servo, so you can go in and play with it and see it in action. So all the theory you'll see today, you can actually experience it right after. And so without further ado, I'll introduce the team. Waterloo is a student team from the University of Waterloo, Canada, focused on advancing student rocketry through practical engineering challenges. The team has competed in the intercollegiate rocket engineering competition, IREC, which is SAC, since 2011, and has achieved significant success, including multiple first and second place finishes in the 10K and 30K SRAD hybrid categories, which is quite a feat. The team has also participated in Launch Canada since 2023, so we're very happy to have them here again. And the team's latest project, Borealis, is a bipropellant liquid rocket with air brakes designed to control the rocket's final apogee, and it aims to validate blood transfusion processes in a high-G environment. You couldn't pack more technology in one rocket. It's fantastic. The team thrives on collaboration and learning, providing hands-on opportunities for around 100 members from diverse academic backgrounds in research, design, analysis, and testing, as skip one, fabrication, throughout the engineering design cycle. So representing the title, Implementation and Verification of Active Altitude Control Systems, we have Richard Ding, which is a control subsystem member, who's a second-year mechatronics engineering student, and Armaan Sengupta from controls. He's from the control subsystem member, second-year mechatronics engineering student as well. Please, a warm round of welcome.
All right. Oh, you're back
there, but there's a portable. I can get this one.
That would be great.
Oh. You can share.
Oh, we can just share this one. We don't need.
Okay.
As you prefer.
Okay, sure.
Awesome. Thanks, guys. Hopefully you're having a good evening. Second day of Launch Canada. Hope everyone's excited. So we're going to get into our air brakes, like the man mentioned. So we'll get right into it. I'll pass it off to Richard to tell you a little bit more about the team and motivate why we're doing the air brakes in the first place.
Okay, so we already talked a bit about the team in the introduction, but I'll just quickly recap already. Okay, so we are a student design team from the University of Waterloo, and we were founded in 2009 and competed at IREC back in 2011, starting 2011, and we are composed about 100 students from 4 different faculties. That's engineering, math, art, and science. And for this year, we have a liquid bipropellant rocket with ethanol and liquid NOx and Borealis. Okay, so a bit about our past achievements. Last year, we entered at Launch Canada with a mini Carrington of the Sky, which is the team's first solid rocket. And we have also competed with Levanza of the Sky, LOTS, which achieved an apogee of 31,476 feet, which is the closest to the predicted apogee of any 30K hybrid at the Space America Cup. Okay, so a little bit of background and motivation of why we are putting the airbrakes into our rocket. So as you saw in the previous slide, the Levanza of the Sky was only 1,000 feet, a bit more than 1,000 feet off from our predicted apogee. And it's really hard to close this gap even more without dedicating significant amount of time on passive designs, such as sending the rocket to a higher grade, or do better on the painting, or working on our simulations. So instead, we decided to implement an active control system with airbrakes. Inspiration. So here's our inspiration. So by the nature of rocket stability, I think most of you here are pretty familiar with the concept of center of pressure and stability in calibers. But when we try to place airbrakes in the rocket, it's better that if we try to put the airbrakes towards the rear of the rocket, because then the surface area will introduce backward shift in the center of pressure on the overall rocket system. And by that means, the rocket actually becomes more stable when the airbrakes extend. However, we cannot do that because we always compete with a hybrid or liquid rocket. So anything below the center of gravity is basically being taken up by the entire fate system. So which means our airbrakes must go above the center of gravity, and that introduced two issues. One is stability concerns, and the second is interference with the fins. And also because we have a liquid rocket, we don't understand very well about the engine and its aerodynamics, so that's introduced additional difficulties in simulating this rocket. The good thing is the team knows OpenRocket very well, so we can use OpenRocket to do a very early study of how the airbrakes will behave on the rocket. So there's two things we are trying to get out of this study. One is we need to determine the location of where we put the airbrakes and also the rough size of them. And secondly, we to validate what is the minimum stability that our airbrakes will induce on the rocket. Okay, so from our last year's rocket, Leviathan of the Sky, we know that the deviation from the predicted apogee from OpenRocket is about 3% from what the actual apogee we reach is. So ideally, the airbrakes should be able to take this entire apogee difference out. So our altitude prediction for this rocket as a very early design cycle was 24,100 feet. So ideally, we should try to be able to do plus minus 1,000 feet of control with our airbrakes. So in OpenRocket, we can't really model airbrakes, but we can do 3 disks, which will introduce additional surface drag on the rocket. So we will have 2 sets of 2 rocket models, one with those 3 disks and one without the 3 disks. And we run the simulation in between. So when we change the size of each of the disks, we will change how much drag they produce on the rocket and how high the rocket will go. So we played around with those settings, and we found out that 3 circular disks that's between the diameter of 1.1 to 1.2 inches gave us the desired control regime we are looking for. Okay, however, those disks does not have any effect on the center pressure, so we took some way to validate that the center pressure is in the location we want. So we found an online study which tells us that the center pressure for a flat disk that we used is roughly 2.2 times in diameter behind the plate. So we can use a massless cone. We can place that cone at where we think the center pressure will be to force the center pressure to that location. Then we can run the entire simulation to see if what the stability is. Okay, so the results are really good. The airbrakes only reduce the stability margin by 0.19 calibers in the worst case, which is really easily mitigated if we just change the fin sizing. Okay, but only OpenRocket is not nearly enough for what we are trying to do. So instead, we are going to the domain of CFD using Ansys Fluent. So we need to do some analysis to check 2 things. One, we need to classify our drag across a range of different altitude and velocity, and we also need to check on the aerodynamic effect, such as when the air flow over the airbrakes, how will it affect the airflow over the fins. Okay, so CFD is basically divided into 3 subsections: geometry, meshing, and solving. So we start with geometry. It's basically just creating an enclosure around the rocket, subtracting the rocket itself. So we are only left with the air molecules that are surrounding the rocket. And we are also adding body of influence around the airbrakes, nose cones, wherever there's a smaller geometry that we want to be more accurate about. And next, we get into meshing. We did a mesh refinement study, which basically optimized the solving time versus the accuracy. We try to find a balance between the two. So it comes down to polyhedral mesh with 5 boundary layers, and those are the target mesh qualities, which both fall into the excellent region recommended by Ansys. So here you can see a picture of our mesh, including the body of influence and the boundary layers beside the rocket. So the solving uses a SST K omega model with a velocity inlet just being the rocket velocity, because we cannot move the rocket around. So instead, we make the air flow around the rocket at the velocity that the rocket is going at. And we also set the altitude by changing the air density and viscosity. The pressure outlet is just 0 gauge pressure, and the roughness for the walls, for the rocket walls, is just how much our painting roughness is. So the result for drag is pretty trivial. You just click 2 buttons in answers and it displays you like how much drag there is on the rocket. Center pressure is a little bit of different because that's like the weighted average location of the pressure distribution along the rocket surface with the pressure acting at each point being multiplied by the distance from a reference point and divided by the total pressure. And that gives you the center pressure from that point. And that's an equation we to enter into OpenRocket, into answers and ask answers to solve for us. And we also draw some contours and streamlines along the rocket to make sure like the airflow is fine. Does not interfere with the fins themselves. Okay, so initial verification against OpenRocket. We to find some sort of correlations, correspondence between OpenRocket and answers to make sure like no one simulation software is straight up lying and give us false data. So we decided to simulate loads, elevation of the sky, our old rocket in answers, compare that to OpenRocket, because we already know that elevation of the sky is simulated really well in OpenRocket. So we decided that like, the two will match if the drag is within 5% and the center pressure is within 5%. And the result was even better. The drag was in 3% difference, and the center pressure was within 2.5 centimeters, which means that this CFD model can be applied to solve for our new rocket. So we need to double check if we have enough drag, which is done by modeling a very simple geometry with Borealis, 3 fins, 3 airbrakes. Rocket length is taken from the flight dynamics of our CAD. And the results confirm that there is sufficient drag for the control regime we are trying to achieve. And last thing is checking for the worst case stability. It's basically when we like took a range of parameters such as altitude, velocity, angle of attack, and we just hold the other constant. We'll try to simulating for one, and we combine them together in the worst case, which is the case shown here. And that gave us a center pressure of 3.169 meters from the nose. And that value is being passed along to flight dynamics to set the fins. And with that, I'll pass it to Armaan to talk about the mechanical design of the airbrakes.
Awesome, thank you, Richard. Yeah, so now that we've validated that the airbrakes are indeed going to be stable and have a rough idea on how big they need to be, we can get into start designing the actual practical implementation for how they're going to manifest. So there are 3 primary constraints that we wanted to put upon the design here, and you can see them on screen. The 2 I want to highlight is number 1 and number 3, because those are actually pretty hard to come by in a singular mechanism. So we're going to talk a little bit about how we achieve that, but let's just get into the nitty-gritty of it and let's move on. Okay, so we considered 2 primary designs in the beginning, kind of based on what teams had done in the past in terms of air brakes. And this was the first one. It was mocked up by a team member. And only the real issue with this one was that the primary load from the drag placed by the panels would be primarily exerted on the motor, which means the motor would have to be pretty strong or have some kind of lockout mechanism so that it's not constantly under load. Whereas if you compare to the second version of this, more like a pancake design, the load is isolated from the motor, meaning the motor does not have to actively try to keep the panels where they are, despite any amount of loading from the drag. So we ultimately ended up deciding to go with the second design, and I'm going to go into a little bit more detail about specifically how we implemented that. Okay, so one really important thing that we wanted to try to achieve was having a linear control regime. So a certain amount of rotation translates to a linear amount of extension. We did that by parametrically modeling a curve in actually Desmos, like you can see on screen, and then implementing that within SolidWorks so that any amount of X rotation leads to Y translation, and that ratio stays consistent for the entire rotation, which makes the control system easier to implement. Okay, I'm going to kind of speed through this because I know we're running out of time a little bit here. We have a lot of different mechanisms here within the air brakes to reduce friction and reduce and isolate any loads onto the servo. What that essentially enables us to do is the servo does not have to be nearly as strong as if otherwise had to withstand the loads from flight. And any loads that do come into the servo are taken care of by the structure rather than going directly into the servo. And the 3 primary ways we've done this is with linear bearings, our bearing stack at the top, and then a very strong radial bearing in the center of our plate there. A few renders here. You can see that the other criteria, so we talked about how we achieved criteria number 1 and number 3. The other criteria number 2, which was being lightweight, hopefully is visible here as well. You can see that it's pretty compact and lightweight, so I think we've done well in achieving the goals we set out to. All right, quickly going to talk about integration here. I think there's one really interesting thing compared to how most things are integrated in rockets. Normally you have bolt circles and couplers, which we do, but we actually saved out on a bolt circle by not having the air brakes radially bolted into its body tube. Instead, we clamped on two flanges, which isolated, which prevented its rotation, translation along the length of the rocket, and then we used clocking to prevent its rotation, thereby locking it in all 6 degrees of freedom without requiring an additional bolt circle. So I thought that was pretty interesting. Finally, based on the expected values, which Richard's going to talk about a little bit more in a second, for how much force we expect the panels to experience, we did loaded and unloaded testing and found that the air brakes survived quite well. They were robust even under loads and worked for long periods of time without any noticeable side effects. So I'll pass it back to Richard to talk a little bit more about how we calculated the drag curves for various different operating conditions, and that's going to become very relevant for a lot of the firmware I'll talk about later.
Okay, so now Armaan have designed the geometry of the airbrake system to get a final drag lookup table for our rocket. So basically, I created a geometry for the new rocket Borealis, which includes all the surface finishes, which are like the bolt circles, the surface details, and the new fin shape that just got produced by Flight Dynamics. And with that, I simulated those geometries at the following conditions, which is at different extensions, different altitude, and different Mach numbers for velocity. Well, manually setting up each case and waiting for it to solve will basically just mean death. Because if you think about it, there's 10 extensions. At each extension, we to simulate for 16 velocities. And at each velocity, there's 10 altitude, which summarizes to 1,600 cases. And if we just have one team member sitting there trying to wait for each case to solve, and then trying to like plug in the next value, it will take 4 hours. So instead, we utilize PyAnswers, which takes all the case settings from a CSV file, calculate for all the values. For example, when it takes the altitude, it will use an online calculator to solve for the viscosity and density of the air and plug that back into the answer solver. And it will dump all the final solutions into another Google Sheet CSV file for me to look at. Okay, so the solving time, that is a hardware we are using, a supercomputer from our department, and it takes 53 hours for the entire simulation to run once. So there really isn't much of a margin of error over here. Okay, here you can look at the graph. That's all of our drag simulations at each different extension. That's a 3D graph with velocity, altitude, and drag value. And you can also overlay them on top of each other, which basically shows you how unlinear the entire drag system is, which means we cannot just like solve for one, then scale them for the other ones. And although we have those surfaces, we do have some ways to pass them to our controller, to our control system. So we did a polynomial interpolation of all the data on a surface, and that gave us an equation which we can just like plug and use. So here is our drag force in answers was open rocket. You see the line that above is supersonic, and the two solvers like behave really differently in supersonic speeds. So we could do some more like data processing in those areas. But for any velocity that's like below supersonic, you can see the two matches up really well. Okay, and with that, I'll pass back to Armaan for the processor board and firmware.
Thanks, Richard. Keep it. Yeah, so thanks so much, Richard. And that's really going to be very helpful. And when we talk about trajectory prediction in a second here, processor board is essentially where we do all the computation. And the primary goal of what I'm going to be talking about for the next few minutes here, because we don't have a lot of time left, is going to be how do we take raw sensor data and then determine how much we want to extend the air brakes. That's the ultimate goal here. So the first way we do that from a high level perspective is we are using an RTOS, and on that processor board I showed earlier. And what that's really effective in doing is we have several tasks. Those are the ones highlighted in blue. And we are going to be communicating between those tasks, and those are the buffers highlighted in green. And so what this allows us to do is have a good modular system, and it makes it easier to conceptualize, debug, and just generally develop code when you can break it up into bite-sized chunks. Specifically, I'm going to talk about 3 systems here. So the first one is going to be state estimation, and then that's going to feed into trajectory prediction, and then finally into controller. So getting right started with state estimation, this is what directly deals with the raw values from our sensor, specifically the VN300, thank you, Vector Nav, that allows us to basically figure out where our rocket is pointing. We implemented a magic filter, and if you're interested, there's some more links below the slide where you can go learn more about that. But from our experience, we found that it is less computationally intensive while having less drift compared to more traditional filters such as a Kalman filter. So we found it worked really well, and we're very happy with it. And this is exactly how we're going to figure out where our rocket is pointing. We're then going to take that information about where the rocket is pointing, and along with our current altitude, which we get from our altimeters, we're going to determine where we think the rocket is going to go. And we do this by solving a set of differential equations. They're on the bottom right of the screen there. While they're easy to lay out, they're not so easy to solve by hand at least. So we use numerical methods, specifically a fourth order Runge-Kutta method, to be able to solve that set of differential equations. And what that's going to do at each time step is it's going to give us our velocity as well as our height. So all we do is we look for when our velocity goes to 0, that's apogee. And then we say what is our height at that point. That's our predicted apogee. Now that's going to be really important for the final part of this pipeline or this layer of which is our controller. So our controller is then going to look at the difference between what we think our predicted apogee is and our apogee that we report to Launch Canada. So that's our target apogee. The difference between those two things is our error, and the controller is going to effectively try to minimize that error. The way we're doing that is with a PID loop, but I think what's more interesting is how we actually tuned that. So we created an OpenRocket plugin that effectively allowed us to monitor the response of changing these parameters within our controller and seeing how the rocket would respond. So we're effectively able to use the current state of the rocket to influence our trajectory prediction, which then, like I mentioned, influences our controller. This gives us an extension value based on the polynomial drag curve that Richard talked about, gives us a new drag, which we then override in OpenRocket. That updates the current state in OpenRocket. Around and around we go. And that's how we come up with these coefficients that allow us to tune our system to be very accurate and have minimal oscillations. And so with that, that is a total system overview. I know it was lengthy, but I hope you guys learned something. And I wanted to just give a big shout out to our sponsors who we would not be able to do this without, especially on the air brakes. That's going to be ANSYS and VectorNav. This would be, you guys are indispensable, and we wouldn't have been able to do this without you. So thank you so much to our sponsors. And thank you so much to all of you guys for sticking us for this evening. And hopefully you learned something. Glad to take any questions. Time.
Thank you. Great presentation. Very complete. Do we have any questions from the audience? All right. I knew this one would be popular.
Hi. Yeah, great presentation. Really liked the whole process from analysis to design and testing. I was wondering what the load path of the drag looked like through the pedals and into the airframe.
Yeah, sure. Does this one work? Yeah, perfect. Okay, so that's helpful in this diagram here. You can imagine the panel is loaded. Its worst case would be when it's extended fully out. You get a pretty big bending moment on that panel. So that is primarily taken up by your linear rail. That's bottom left there. Those rails are rated for above 15 pounds, which is the max force we took, and that converts to some bending moment over whatever that distance is. So that's the primary mitigation of that load. It goes through that linear rail. In terms of other potential side loading that we might, or not, these are hard to characterize, but could happen in any given way, that servo shaft is then protected by any kind of side loading by that a really strong radial bearing in the center of that plate. Does that answer your question, or are you going in a different direction? Good, awesome.
Thank you for the presentation. Can you go to the slide with the CFD mesh setup?
Yeah. This one?
Maybe it's one next slide.
Next. Okay, this.
Yeah. So you're trying to resolve the entire rocket. That's what I get. It's not,
Yes, that's the entire rocket.
Okay. How fine is the I see you added the body of influence.
Mm-hmm.
How fine are the mesh there? What's
Okay,
the
yeah.
size?
So for the body influence, it's all about the mesh refinement study. If you are interested, I can send it to you later. But for the body influence, it's anywhere between 1 millimeter to, to 3 millimeters. And for the overall rocket, it's in the centimeters range. So we are trying to strive a balance between how accurate it is, how many skewed cells, how many orthogonal cells there are, versus how fast each iteration solves. Because we do to solve for 1,600 cases, which means we can really spend a long time on each case.
Yeah, thanks. And for the boundary layer.
Mm-hmm. Yeah.
Yeah. No, go back to the meshing, please. Yeah.
Okay, sure. This one.
I can see it's not very fine there.
It's 5 layers of boundary layers. I just didn't zoom in enough to like look at the details. I think.
So you did, I guess, want to resolve the boundary layer. Did you use a wall model or just try to resolve the entire boundary layer?
It's just a normal type of boundary layer. And, like there's a setting for that. Just add how many layers you want.
Thank you.
No problem.
Actually, I have a follow-up question on the Gabriel's question a little bit earlier. So we've seen at SAC a few times some air brakes, and as I mentioned a couple of an hour ago now, that we've seen often some catastrophic decomposition of the rocket in flight because of the air brake system. And one thing that I see teams often forgetting is that at a high altitude you do get crosswinds. And so while yes, you're going in a certain direction, when you're opening your air brake and you have unsymmetrical crosswinds, you actually do generate some lift asymmetrically on the rocket, which causes you to a little bit drift in the air, and it causes that lateral motion. And teams don't necessarily always think about what's the structural implications of that on the whole rocket. Yes, on the air brake, but not on the whole rocket. So first question is, have you thought about this consideration? And second, what are your acceptable launch conditions and wind conditions to be able to deploy your air brake?
Okay, so if I understand your question correctly, you're saying if the rocket pitches over, what are the loads that would be imposed on the air brakes, and have we considered that?
Yes, and the follow-up is essentially, what are your conditions acceptable for launch?
Okay, so I definitely can't talk to the second thing. That would be more of a flight dynamics question. I can't speak too much to the flight conditions before launch. I can speak a little bit more to the first part of that, which is what are the additional loads on those air brakes. In terms of, yes, the most obvious load is what I answered the gentleman's question over there, which is the direct force of drag load. However, we have looked at other load cases. So for example, I mentioned the radial bearing in the center. Technically, when you get under load with symmetric loading, that is unloaded, so that bearing wouldn't be necessary. There would be no load on the servo. But for extraneous conditions, for example, when you have asymmetric loading, like you mentioned, that would then produce a moment on the shaft of the servo itself. And so that's why that radial bearing in the center is required. And so, yes, we did make consideration for things such as that, and just generally try to have a more robust system in ways that, like, you might think, oh, that's not necessarily exactly how it's being loaded now, but trying to think of ways that it would be loaded just in general, and make sure that things can't break if you push it a certain way, even if that's not the nominal condition for flight. So I think that's one example. I don't know if that's quite the direction you were going, though.
That does answer the question regarding the actual air brake system, which is often the focus of design. My question is regarding integration with the rest of the rocket, the body tubes, the couplers. Can they take the loading caused by the air brake system in an asymmetric profile?
I see. We have primarily looked at symmetric loading for that condition, and we have done mostly back of the napkin calculations on like shear stress or the bolt planes that connect to the UBT and the vent section. We have also looked at, I believe, bending moments, but we do that as a general study for the rest of the rocket, and the interface between the air brakes to the UBT and the vent section is not very different than a lot of the other interfaces we're very used to in the rocket. So it's a very similar thing, and so we applied the similar design validation philosophy to that. I wasn't quite too involved in that, but the airframe people would have done the exact same kind of validation because it has the same interface with it. But you're correct in that it could create further loads that were unexpected due to the additional panels. I can't quite answer how much I think we've looked into it, but we definitely have a pretty heavy safety factor on the bolt circles that connect between the couplers of the rocket.
Perfect. My recommendation would be to be careful with crosswinds at high altitudes then.
Yeah.
Any other questions? Wonderful. Oh, yes. We're going a little jog. Here.
Thank you very much. Good presentation. Mine's just a brief question. On one of your slides, you were comparing the open rocket to your ANSYS simulations for drag.
Yeah.
And you reported a discrepancy in the reported drag for the supersonic regime between open rocket and
Yes.
ANSYS. For my first question is, do you know how open rocket models the supersonic regime? Does it actually capture the increased drag due to the shock interactions on the rocket?
Pardon? Can you?
Sorry. do you know how OpenRocket is capturing the extra shock drag that you encounter in a supersonic regime?
Yeah, that is something the team is not very familiar about because like most of our work, like most of the flight takes in the subsonic section. So like the supersonic section was like really analyzed, which means we don't know much about that. And to deal with that, we do place a lockout on the rocket, which basically says we do not actuate the airbrakes until the speed fall back to the subsonic speed, which combats with the problem.
Okay, because yeah, the other part of my question was, were you resolving your mesh enough to resolve the shocks?
Yes.
That would be present in a supersonic flow, but you're kind of circumventing the problem by operating it only in a subsonic regime.
Yes, and that's like a thing we to like deliberate because the earlier we actuate the airbrakes, the higher control regime we have. But at the same time, there's more uncertainty, there's more like unknown aerodynamic effects we don't understand with supersonic, which means we to like try to find a balance in like the two.
Nope, that makes sense. Thank you very much.
No problem.
Beautiful. A round of applause for Waterloo, please. Thank you. So this concludes the presentations before lunch. It is now the lunch break. So please proceed to ingesting food. And